All systems operated successfully with an engine firing duration of 30 seconds. Subsequent run times will increase until full duration is reached, with cutoff and restart as programmed for the two-burn Centaur. Centaur is under the direction of NASA's Lewis Research Center, Cleveland, Ohio. Lewis engineers provide special support for the program, which can best be accomplished at the advanced facilities available at the research center. One of these support activities utilized NASA's Space Power Chamber for altitude tests of the balanced vent system. The facility simulates altitudes up to 100,000 feet, subjecting the vent system to conditions close to space operation. Early tests measured net thrust and the flow rate and pressures at the exit nozzles using helium gas. Data from these provide support for more advanced testing at cryogenic temperatures. The test series started at sea level pressures to simulate ground venting. A mid-range test simulated vent operation between 35,000 and 40,000 feet. Advanced testing simulated altitudes between 90,000 and 100,000 feet, closely approximating the conditions of coast phase flight. In another area at Lewis, a series of tests investigated the effect of propellant slushing in the Atlas fuel tank under abnormal amplitude conditions. For these, a quarter-scale Atlas fuel tank was mounted onto the NASA experimental slush force test bed. Test sequencing simulated slush amplitudes, which have an adverse effect on launch vehicle stability. In one series, the tank shear membrane was in place. The second series of tests investigated slush characteristics within the tank with the shear membrane removed. Results from the two series will be compared to ascertain the effect of this membrane on slush motion. The evaluation will lead to a more precise definition of the vehicle's stability margin. With most of Centaur's systems proven, research and development for the project centers upon product improvement or refinement of data. Convair's environmental test laboratories play a key role in this continuing task. For example, in one project, a technician subjected samples of Teflon to thermal shock. This material is used as a seal in the liquid oxygen vent duct on AC-8. A total of 24 samples went through the cycling process. 12 of them, varying in thickness from 2 to 20 mils, were control samples, not subjected to thermal shock. An identical 12 were cycled in and out of liquid nitrogen 200 times, exposed 5 seconds to a temperature of minus 320 degrees, and 10 seconds to room temperature. A weight at the bottom of the sample loaded it to 780 pounds per square inch. Objective of the dip tests was to determine the effect of thermal shock on the tensile strength of the material. After dipping, samples were tested to destruction in another lab. Variables were elongation of the samples and the force required to break them. For 20 mil samples, there was no significant difference between those subjected to thermal shock and the control samples. Thermal shock had little or no effect upon the tensile strength. For thinner samples, data produced surprising results. Thermal shock samples proved to be stronger than control samples. A possible explanation of this phenomenon is that the Teflon, under constant load thermal shock, undergoes a uniaxial alignment of its molecules. The actual mechanism which causes the increased strength could be established by tests such as X-ray diffraction or measurement of optical characteristics. In another study, engineering began a detailed study on characteristics of flexible linear-shaped charges at different temperatures. In this case, the shaped charge is a V-shaped strip of metallic sheath explosive used to cut loose flight hardware for jettisoning. When detonated, the explosive force travels vertically from the flat inside surfaces. At the point of intersection, the forces redirect themselves into a cutting edge which knifes through the material at a 45-degree angle from the initial direction of force. The material for the tests was a metal plate grooved to produce a sample providing metal thickness over a wide range in the one sample. The charge, which duplicates flight hardware, is encased in a strip of laminated fiberglass, spaced to provide the required distance from material to be cut. The strip which houses the charge mounts to the flat side of the test samples. A series of tests provided data on samples exploded at room temperature and at cryogenic temperatures. For cryogenic tests, plate and charge are installed into a double-jacketed cylindrical container. Liquid nitrogen flows through the outer jacket. Liquid hydrogen, at -423 degrees, flows through a cooling tube, which is in contact with the plate of the specimen, cooling it to about -400 degrees. When the sample reaches the proper test temperature, the charge is detonated and instrumentation records the results, primarily the time intervals at various points along the charge. The sample is examined for depth of the cut, then compared with previous samples for consistency. To date, there has been no significant difference noted between tests at different temperatures. Using the same apparatus, tests have been run to determine the ability of the charge to jump gaps in the test specimen. This test fixture is an air-bearing device used for simulating the separation of Surveyor from Centaur. The simulated Surveyor is suspended from an overhead frame supported on knife edges mounted to the retromotor. The complete assembly slides on nearly frictionless air bearings. Surveyor attaches to a Centaur adapter, which includes an electrical disconnect mechanism, separation latches, a switch that senses an inadvertent separation, and the springs which push the spacecraft free of the booster in space. Tests were initiated by a laboratory programmer. Instrumentation measured axial acceleration, pitch and yaw movements, and precise timing of events. The main variable used for these tests was a programmed relocation of the center of gravity between operations. Results of tests at this stand verified the proper functioning of separation components. At the end of 1965, operational Centaur AC-7 was on standby at Complex 36A, Cape Kennedy, Florida. AC-8, a two-burn research and development vehicle, was in final stages of assembly at Convair. It was scheduled for shipment to Cape Kennedy in January. Also in final assembly was AC-9, the second of two Centaurs that will fly a two-burn research and development mission. AC-10 is a single-burn operational launch vehicle. It is an advanced vehicle with improvements in guidance. The additional ground testing required for the SC-1 Surveyor vehicle has resulted in a rescheduling of the first operational Surveyor flight. As a result, Lewis Research Center directed Convair late in this report period to return AC-7 to San Diego for updating and to combine SC-1 with AC-10 for CSTS operations and the subsequent launch. Of the remaining Centaur vehicles under contract, all 5 were in production in various stages of fabrication. AC-11 will fly a one-burn direct descent operational mission. Beginning with AC-12, all subsequent vehicles will fly two-burn missions. In the year ahead, the major emphasis for Centaur will be on manufacturing, acceptance testing, and flight, and studies involving advanced applications. In 1966, Centaur will become a fully operational space vehicle for both the single-burn and two-burn missions. During the year ahead, a Surveyor spacecraft will land on the Moon to transmit our first close-up views of the lunar landscape.